This is a continuation of section 15.1, and this is the double integral part. So for example 3, we have the double integral over r of cosine of x plus 2y dA. Now dA is going to be either dx dy or dy dx. And it doesn't matter. This is the range on x and this is the range on y. And so then this order here doesn't matter. If the domain is rectangular. So in general, it does matter, but for these specific problems from this section, it doesn't, because what our domain is, our xy plane that we're going to project up onto the surface. And this integral, what it does is it finds the volume underneath the surface cosine x plus 2y, but over this rectangular region. I better put an outline on here. This right here is R. Okay, so since it's arbitrary, I'm just going to go ahead and set this up as the integral from 0 to pi. So that's my x. And then the integral of 0 to pi over 2 of cosine of x plus 2y. Now for dA, since this inside integral goes with the y values, we're going to do dy, then dx. We're going to integrate this inside integral first. Let me go ahead and highlight that this is what we're doing here. Okay, and so we're going to, what we're really just doing is integrating twice. Now, when we integrate with respect to y, we can treat x as a constant. So when we take the integral of cosine of x plus 2y dy, what we get is positive sine of x plus 2y times, we need to do like the reverse chain rules. So the 2y, we need to multiply by 1/2 here. And that's it. Then we have dx. Actually, that's not it. We need to put in the limits of integration from 0 to pi over 2. So the next step is to put in those limits. So I've got the integral from 0 to pi. Now, you have to be a little bit careful here because you have two variables. These are y values. This is y equals pi over 2 and y equals 0. So I'm going to put in sine of x plus 2 times pi over 2. So that's x plus pi. Times 1/2. I forgot about my 1/2, but I'm going to go ahead and put the 1/2 here. And then we're going to have minus sine of x plus 0. So just x. And then this will need a dx. So I really need to put this 1/2 outside because it does affect this second part. So I'm going to go ahead and write it out here. 1/2 integral 0 to pi. And I don't think there's anything to clean up, but I just want to be careful. X plus pi minus sine x dx. And you do need these parentheses here because of the sum. So now we're going to do the second integral. So our 1/2 is still there. And then we're going to take the antiderivative of sine of x plus pi dx. So that is going to be negative cosine of x plus pi. And then the minus sine x, that will be plus cosine of x. And this is all going to be evaluated from 0 to pi. Next step, I'm going to have 1/2 times. I'm going to put in my limits of integration here. So I've got negative cosine of x, which is pi, plus pi, so negative cosine of 2 pi, plus, did I do something goofy? I did something goofy. Maybe I didn't. We'll see if I get the right answer. Okay, and then plus cosine pi. Then we put in 0, and we subtract. So that's going to be plus cosine pi minus cosine 0. Cosine 2 pi is 1, so we get negative 1. Cosine at pi is negative 1. Again. And cosine of 0 is 1. So it looks like I'm getting 1, 2, 3, 4. I'm getting negative 2. And that's the correct answer. So we're good. The next example that we have here is going to be really similar. So I'm going to go ahead and leave it to you guys to try, and we'll do it next time in class. This next example, example 5. It's actually a little rule I want to give you. So this is for a surface that can be broken up into the product of a function in terms of x and a function in terms of y. And it has to be over a rectangle. So you need those two conditions to use this theorem. And the theorem says that if you have integral a to b, integral c to d of g of x times h of y, and this would be dy dx, that's the same as the integral from a to b of g of x dx times the integral from c to d of h of y dy. It's just very important that we point out that this doesn't happen generally. You have to be able to split this up into a product, and it has to be over a rectangle. So you know that it's over a rectangle if A, B, C, and D are constant. Okay. So for this example here, example 5, you can see that y to the negative 2 is a function of y, and then e to the 2x is a function of x. So this is perfect for using this theorem. We can separate this, the integral from 1 to 4. Now notice what the one that I took is the outside one. So from 1 to 4, that is dy, and that is the yellow. So the 1 to 4 is the outside, it goes with dy. And so we've got y to the negative 2 dy, and then the other integral is going to be the integral from 0 to 2 of e to the 2x dx. And when you integrate these, we're going to, let's see, add 1 and divide. So we're going to have negative y to the negative 1 evaluated from 1 to 4 times 1/2 e to the 2x evaluated from 0 to 2. So here we're going to get negative 1/4 plus 1 times, when we put in the 2, we get, let's see, we get a 1/2, and then e to the 4th minus e to the 0, which is 1. So we have 3/4 times 1/2. So we're going to have 3/8 e to the 4th minus 1, which is the correct answer. This last example is sort of an application. We're going to find the volume under this surface. Take a moment to figure out what that surface is. It is a hyperbolic because of this one negative sign, paraboloid. So this is the one where we have this going on. There's a hyperbolic paraboloid. So it's not always super important to know what the surface looks like, but I think it's good to have like some idea, and sometimes it is really important when we have to sketch these out. But volume is going to come from doing the double integral over r of 4 plus x squared minus y squared dA. And so we just need to put in our limits. And again, because we have a rectangle, it doesn't matter. The order doesn't matter at all. I'm going to go ahead and do from -1 to 1 on the outside, 0 to 2 on the inside. We've got 4 plus x squared minus y squared. And then the order in which we picked our limits, our first one is 0 to 2, that's y. So we're doing dy, then dx. Let's go ahead and compute this inside integral. So I've got the integral from -1 to 1, and then the integral of 4 dy is 4y. The integral of x squared dy is x squared y. And the integral of negative y cubed is -1/3. I'm sorry, the integral of negative y squared is negative y 1/3 y cubed. And then this is all going to be evaluated from 0 to 2. And then after we're finished with that, I should have put dx here. Okay, so now we're going to put in the limits of integration. And what I can do, I can put them in. So what I'm going to do is for 2 minus 0, especially for polynomials, this is the way to go. I'm just changing the order in which I plug in my limits of integration. Plus, I've got x squared, 2 minus 0, minus 1/3, 2 minus 0 cubed, dx. So I think I have the wrong parentheses here, but that's okay. Or it's not okay. Okay, so I've got the integral from -1 to 1. This is 8 plus 2x squared minus 8/3 dx. And so then when I put in those limits, or when I integrate again, let me not get ahead of myself, I'm going to get 8x plus 2/3 x cubed minus 8/3 x, which I could have combined, I just saw, evaluated from -1 to 1. And now we've got, let's see, 8x minus 8/3 x, that would be 16/3 x. Let me go ahead and clean it up before I do that, before I put in the limits. And this is from 1 to -1. I'm going to do that thing again. So I'm going to put in the 1 and the -1 instead of putting, I'll show you right now. So I'm going to put in 1 and then do the minus -1. And then plus 2/3. If I put in the 1 and then minus the -1 cubed. This is the same. We could also do 16 thirds times 1 plus 2 thirds times 1 cubed minus the 16 thirds times -1 plus 2 thirds times -1 cubed. So in this is probably how you're used to doing it, where this is where x equals 1 was put in. And then the other side is where x equals 2. Whoops, wrong thing. This is where x equals 2. I'm sorry, not 2, but -1 was put in. And in this case, we just put it in there. And so we should get the same thing either way. Just changing the order that the addition happens in. So this is 2 times 16 thirds, which is 32 thirds. And then this is 2 times 2 cubed, so 8. So that's 16 thirds. And 32 and 16 is 48 thirds. And I'm going to hold my breath because that's not the right answer. It should be 12. See, is that example 6? No. It should be 12. Oh, wait. Is 48 divided by 312? It might be. Yeah. Hold on. No, that's 16, isn't it? It should be 12. So let me just check what I did here. I may have, not sure. I'll let you do it. I think that I'm looking at my notes and I'm fairly certain. Let's see, the 2x squared plus 16 thirds. I have a slightly different thing here. So let me just look over. I'm not sure. It should be 12 though. Go ahead and try it on your own, and we will go over it next time in class if there are any issues. You'll probably find it right away. That's it for this section. This was 15.1. And I'm going to go ahead and post this because I've already done it too many times. All right. Thank you.